Welcome to part 2 of our notes on, ozone. So ozone notes part 2. Well, we're going to begin today by talking about the good, the bad, and the ugly about ozone. Now, the good ozone is located in the stratosphere. This stratospheric ozone is created when UV radiation strikes a diatomic molecule of oxygen, O2, and it breaks oxygen into two single atoms of oxygen. These individual atoms of oxygen are very reactive, so they'll readily combine with another diatomic O2 molecule to form O3. So let's take a look at that. Here I've got a chart or visual of it. So you can see UV radiation striking this diatomic molecule of oxygen. Again, it's got two oxygens. And it'll break it down. It'll break it into two individual oxygen elements. And this atom of oxygen does not want to be by itself. It doesn't have a full outer shell. It's reactive. So what does it do? A lot of times it will combine with a nearby diatomic molecule of oxygen. In other words, there's two of them. And then this third one will come in, and voila, you get ozone. So that's how ozone is created in the stratosphere. And again, this is the good ozone. Now the bad ozone is located down here. A lot of times it's called ground level ozone. And it's located close to the Earth's surface and is bad for the environment. It contributes to the greenhouse effect. It enhances it. It's also the chief component of smog. Now it does exist naturally at small levels. However, we as humans, we've added to it when we release things like nitrogen oxides and hydrocarbons into the atmosphere. How do we do this? Well, things like the automobiles, burning of fossil fuels and power plants, refineries. Now the ozone is created when sunlight strikes the nitrogen oxides and hydrocarbons. And if you go to larger communities in Wisconsin like Milwaukee, typically their ozone alert days are on days where it's really bright and sunny out because you need that sunlight to break down the nitrogen oxides to create that ozone. So what's the bad thing about all this? Well, the amount of ground level ozone is on the rise. In other words, we're getting more and more of the bad, and stratospheric ozone is decreasing. We're getting less and less of it. So what depletes the good ozone layer? Well, CFCs are a man-made chemical invented by the U.S. and first mass-produced in the 1950s. CFCs were widely used in lots of different things: refrigerants, insulating foams, solvents. And here you can see a molecule of the CFC off to the side. Here's the large C, stands for carbon. You got your Cl, your chlorine, and then here you have your fluorine. So we call it chloro, that's your chlorine, fluoro, that's your fluorine, carbons, that's your carbon. So why were CFCs used? Well, they're inert. In other words, they were non-reactive with other chemicals. They were very stable. They were also non-flammable. They didn't burn. And they were cheap to produce. So when we put all these things together, scientists really thought they were good for us. We didn't realize that they were bad for the environment until years later. And they're easy to produce. So not only cheap, but they're easy to produce. And they're very useful for many different things. So you can see why manufacturers wanted to use CFCs. Now, are CFCs the only thing that harm the ozone layer? No. Things like methyl bromide that you found in pesticides. That's your bromine that's going to do the harm there. Your halon that you found in fire extinguishers. Both of these release a bromine atom that, when broken apart, it's actually 40 times more destructive than chlorine atoms. So I don't want you to get the idea that chlorofluorocarbons or CFCs are the only thing that breaks down the ozone and the ozone layer. There are other things as well. Now, it takes years for ozone-depleting chemicals to reach the stratosphere. Chlorine and bromine can last for decades into the stratosphere. And that's a problem, because what we release now or today with CFCs, it might be in there for another 10, 20, 30, 40 years. We just don't know how long it's going to take to flush all these out of the stratosphere, the atmosphere. So how do CFCs break the ozone down? So let's go through this step. So step number 1, right here. UV radiation will strike a CFC molecule, and it will release a chlorine atom. Now this chlorine atom, again, is very reactive. It does not want to be by itself. So as you can see, it comes over here, and it comes to the ozone molecule, which is in step 2. And in the ozone molecule, again, ozone is O3, what happens is that chlorine will basically break apart that O3 and it will strip away an ozone or an oxygen away from it. So what you're left with is, down here in part 3, you're left with an oxygen molecule, and you're left with something called chlorine monoxide. And that chlorine will take that oxygen and it will move it away. But what happens is when a free oxygen atom happens to bump in or collide with this chlorine monoxide, that oxygen will strip away the oxygen away from the chlorine. You might think, well, that's a good thing to get that oxygen away from the chlorine. Well, it is good because it does form more O2, and eventually some of that may come in contact with another free oxygen element to form O3. But let's look at this. What does that chlorine do? That chlorine actually comes up here, and once it frees itself from that oxygen, will actually come around and we'll skip right over here to part 2, and it'll actually repeat this process over and over and over and over again. In fact, one chlorine from here to here may destroy as many as 100,000 ozone molecules. So it might be nice that the oxygen did collide with it and stripped away that oxygen from the chlorine, but now that chlorine can keep repeating that process over and over and over again. So here's just a different view or representation of it. It's a different way to look at it visually. I'll give you a second to take a look at it. Again, you have the UV radiation coming in, the chlorine comes off, that chlorine step 2 moves over, and then here it collides with your O3. It strips away an oxygen, forming chlorine monoxide, and then once a free atom of oxygen collides with it, that oxygen will carry away the other oxygen as O2, and that chlorine will come right up here, and it will repeat that process again and again and again and again. So one chlorine atom can break apart more than 100,000 ozone molecules. So why is the ozone hole over the poles? A lot of people have asked that. A lot of people are wondering, if we do all this polluting in North America, why isn't it over the United States? Why isn't it over Europe or the industrialized countries? Well, the ozone hole occurs during the Antarctic spring from September to early December. The strong westerly winds start to circulate around the continent, and this creates something called a polar vortex, which isolates the air over Antarctica from the rest of the world. So special clouds form called Polar Stratospheric Clouds. And these clouds don't normally form in the stratosphere, or any clouds don't normally form in the stratosphere. But these clouds, they're special. They only form under special circumstances. And what they end up doing is they end up concentrating the pollutants that break down the ozone layer. They concentrate those pollutants over the poles, and this actually ends up speeding up the process. So even though PSCs are most abundant during the winter, there is no light over the pole to drive the chemical reaction. So here you can see some high stratospheric, polar stratospheric clouds. Again, you don't normally see these. The clouds don't normally form in the stratosphere. Now look at this. These are the highest flying of all the clouds and only occur in polar regions because you have to have temperatures. Look at this. The temperature in the upper stratosphere dips below a negative 100 degrees Fahrenheit. So over the poles is really where you're only going to get the temperatures to be cold enough to form these polar stratospheric clouds. Now, with the arrival of spring comes an increasing amount of sunlight. Okay. Now, the CFCs, in the presence of UV light, are broken down, releasing chlorine atoms which go on to destroy the ozone. And this role of sunlight in ozone depletion is the reason why the Antarctic ozone depletion is greatest during the spring. So let's just review what happened. During the coldest times of the year over Antarctica, and it happens on a limited basis over the North Pole as well, but over Antarctica, these polar stratospheric clouds form, and they form a vortex. In other words, that cold air sits over Antarctica, and it locks in all those pollutants. Now, because it's so creating a vortex, no warm air can get in. And then you got to remember, in the winter time, there's no light over Antarctica, so these don't break down. The ozones don't break down. They need that light to help this process. But once the spring starts to roll around, and you can see that here in the slide, once spring comes, you start to get that sunlight. It readily speeds up the process. And because it's so cold yet, no warm, fresh air can come in with more ozone. So that sunlight, when it comes in the spring, which is their October, it really breaks the ozone molecules down. And that's the chlorofluorocarbons are breaking these ozone molecules down. But once we start to get a little warmth in there, once the warming temperatures near the end of spring, that vortex tends to break up. And it breaks up around mid-December. So as warm ozone-rich air flows in from lower latitudes, the PSCs are destroyed, and the ozone depletion process shuts down, and the ozone hole heals until that process starts again the following winter. So here we can see that, and we see a picture of this in part 1. So that polar vortex would form over Antarctica, and it would lock in that air, and no warm, fresh air would come in until spring rolls around and it breaks that vortex up. Excuse me. Now, the ozone hole currently covers a region a little bit larger than Antarctica and extends from 12 to 20 kilometers in altitude in the lower stratosphere. And an ozone hole is currently forming over the northern hemisphere. Now, the 1997 ozone levels over the northern hemisphere were 40% lower than 1982 levels. So here we can see northern hemisphere. We can see it going through the cycle, February 12th, 1997, and watch it go up. So we got March 1st, still back in 1997. So watch the colors on top. You can start to see that you're going to start getting some blues. You're starting to see a few purples in there. So you can see that this definitely is not as bad as the Antarctic ozone hole, but it is indeed another area of low concentration. So what is being done? Well, in 1978, the United States banned CFC propellants in spray cans. In 1996, only recycled and stockpiled CFCs were available. So if companies really needed CFCs, they had to constantly recycle them and use them over and over, or they had to stockpile a lot of it. And granted, you might say, well, that's still bad, they still have them. But it costs a company a lot of money to stockpile it. So they've probably stockpiled some, but the key here is they have to continually recycle what they have, otherwise eventually it's going to run out. Today, 150 plus countries have signed a treaty banning CFC productions. Some people talk about volcanoes and oceans and how they release large amounts of chlorine. However, the chlorine from these sources tend to be easily dissolved in water, and it tends to wash out in the atmosphere in rain. Now, because CFCs stay in the atmosphere for such a long time, full damage to the ozone layer may not be realized until 2050 or even as far as 2100. So it may be another 50, 60, 70, 80 years before we understand the full consequences, when we understand what really happened or what's going to happen to the ozone layer. But the good news is, because we've banned these, hopefully in 50, 60, 70 years, hopefully I won't be teaching anymore, but hopefully in 50, 60, 70 years, we won't have to talk about the ozone layer anymore because it'll be completely healed. So here we see just another slide taking a look at global ozone concentrations. Thank you, and hopefully you got all the fill-in-the-blank notes, or the good thing about this being on a video, you can always backtrack and replay it.